All right, so on the other side, if this is the pulmonary side, okay, if we continue that pulmonary vessel through the cardiovascular system, now we're here at the systemic capillary, okay? So now we're in a muscle, all right? So we have a PO2 of 95 that's coming in. That's that slight decrease from passing through the arterial system. But that's still high, right? The tissues, the cells themselves, the PO2 of tissue interstitium is usually around 40, okay? But it can get as low as 1 or 2, all right? In a busy tissue, the oxygen concentration can get very, very small, all right? So the arterial blood comes in and has plenty of oxygen. As it passes by the interstitium, which has a partial pressure of O2 of 40, well, we have a diffusion gradient, right? 95 to 40, so the oxygen's going to flow into the tissues. By the time that blood leaves the systemic capillaries, it's going to match the interstitial PO2, so it's going to have a PO2 of 40. That PO2 of 40 then is what went back to the pulmonary system, and here we are again, right? So we go from 100-ish to 40-ish. Now, intracellularly, so 40 is kind of the interstitial space. Intracellularly, it gets even smaller, all right, 23-ish. In a busy tissue, we can get as low as 4. In a really not busy tissue, it can be as high as 40. Now, interestingly, cells behave just fine even with a PO2 of 1 to 3 PO2 of oxygen, millimeters of mercury of oxygen. In other words, once you get the oxygen into the cells are very good at using every last drop of it, right? And the larger the concentration gradient, physics still happens. So the bigger the concentration gradient, the faster gases move. So if your arterial blood has a PO2 of 100 and your cells are at 1, well, that's a massive concentration gradient. You're going to get a huge motion of oxygen, right? Okay. Now we know that oxygen concentration is going to vary as cell activity varies, right? You know, a busy tissue is going to consume oxygen faster. So that's essentially what this little graph is showing you. Come back here. My always pesky thing I have to move around all the time. All right, so here we have blood flow, multiple percents, right? So this is double, triple, quadruple, and so on. All right. Here we have our interstitial fluid PO2. That is equivalent to, come back here, this, right? The interstitial fluid PO2. Okay, now let's look at how things change as we go across blood flow. So here we are at normal oxygen consumption. So a tissue that is active but not particularly busy. All right. We can see that at a normal blood flow of 100, our PO2 is 40. If we dramatically increase it, our PO2 does go up to about 70, right? Now, interestingly, if we go below 100%, we see that our PO2 starts to fall, right? And at some point, that would be insufficient, and autoregulation would take over and dilate those capillaries and increase blood flow, right? So autoregulation keeps us sort of out of this zone. Now, if we increase the busyness of the tissue, we put our muscle into contraction, let's say, well, it might increase its oxygen consumption by more than 4 times. So what we can see in this graph is that at the same blood flow, if we increase our oxygen consumption, we end up with a lower PO2 in that area for the same blood flow. I think you'll find that's intuitive, right? You know, if you have the same blood flow to a busy tissue, you're going to get less PO2 out of it. Now, what this also shows us is if we increase our blood flow, we can increase our PO2. So if 40 is our quote-unquote normal, Well, if we're 4 times more active, we're going to need 4 times the blood flow to get the same PO2 in that area, right? So this is just showing you that the more consumption you have, the greater blood flow you need to get the same PO2. Top graph is the reverse. This is a sleepy tissue, right? A sleepy tissue needs less blood flow to get the same PO2 because it's consuming less, right? So we can have half the blood flow, 50%, and still have our 40 millimeters of mercury of PO2. Okay, so essentially this is just showing you, proving to you, that oxygen consumption changes the tissue's PO2, but blood flow, increasing blood flow, helps to offset that we can increase the tissue PO2 even in a busy tissue if we put enough blood flow through it. This is why there are so many empty capillary beds most of the time, right? Because for a given tissue, we need to be able to exaggerate the blood flow 3 or 4 times in order to keep our PO2s up. So that means that all around your body you have empty capillary beds a lot of times. But when that tissue is being used, it can get a flood of blood and keep its PO2 up. All right. So you can see why capillary blood flow regulation, that auto-regulation, we talked about it as the vasodilator theory or the oxygen demand theory, right? Both of those are changing this, okay, in response to this. They're changing the blood flow in response to the changes in PO2, right? So if you have a tissue where the PO2 is low, well, autoregulation is going to tend to increase blood flow so that we get the same PO2 present with an exaggerated blood flow.